looking at the notes that I have shared with you. So let me give a quick recap on what we were discussing, and then let us continue with the remaining portions. So let me share the screen. So we were looking at the tropical dynamics. The essence of tropical dynamics is that the dynamics is confined within the tropics due to a very fundamental reason. I begin with that, and a reason which we say that the planetary vorticity changes at the equator, changes the sign or direction at the equator, which causes some restoration potential for dynamics to get confined within the tropics. And to begin with, the treatment was to look at the three fundamental shallow water equations by simplifying the Navier-Stokes equations. We only considered the linear case here. That too, the balance between the accelerated motion, balancing by the Coriolis component or Coriolis force, which is balanced by the pressure gradient force. So these are the basic balances we consider. We did not consider any other balance in the Navier-Stokes equation. And we consider two acceleration in the zonal and meridional direction with a mass conservation balancing the motion. So these three equations give very elegant solutions at the equator. The first one we considered the Kelvin wave because that is of special interest, in which there is no meridional velocity. So we were able to simplify these equations by neglecting a couple of terms in these three equations, and we arrived at a special solution called Kelvin wave. Then later we found that is not enough. There can be much more solutions available. So we assumed the most general form of the solution to this basic equation. We went ahead by implementing the general form of the solution of the form exponential I kx minus omega t in the v equation. First, we reduced the equation in terms of v, and then we simplified those equations. We arrived there are certain definite discrete nature of the solutions possible associated with a parabolic cylindrical function and a Hermite polynomial of order n. We spent quite a lot of time understanding what is this meridional mode represents. So they are quite equivalent to the meridional wave number if you want to interpret it in that way, or it is kind of an eigen solutions in the meridional direction will give you certain eigen vectors or eigen modes of waves. Few of those waves we we have seen in the last class, Kelvin wave and Rossby wave, mixed Rossby gravity wave, Yanai wave. So finally we summarized all those waves in the wave number frequency diagram. I think that is what important. So this is the total number of waves we were able to find out by solving the shallow water equation in the equatorial domain. So the Kelvin wave is a special wave with the Hermite polynomial order n equal to -1. And other waves are, say, for example, meridional mode or the mode n equal to 1 and 2 at a long wave limit. So we separated them into case A, case B. Case A is the long wave limit, case B is a short wave limit. And within the long wave limit, various meridional modes n equal to 1, 2, 3 gives you a Rossby waves whose dispersion curve is to the west direction of the k-axis, implying those waves traveling to the westward direction. And in the case B, in the high frequency side, we found a lot of gravity waves can form, which again have meridional structure n equal to 1, 2, 3. And then we found a special type of wave when n equal to 0. We see that they behaves as a gravity waves in the high frequency side and behaves as a Rossby wave in the low frequency side. So these many wave number, the waves we resolved in the discussion. But we have trouble because there are some areas of this wave number frequency diagram, there are no waves. Say, for example, there is a gap between the gravity waves and mixed Rossby gravity waves. The large region in the spectra, you don't have any waves. Other void region is below the Kelvin wave in the right hand side. There are no many waves there. So why is this is so? Maybe due to the simplified model we adopted. What is our model? The three fundamental equations: two for the momentum equation, one is the mass conserve equation, and so the equations may not be able to resolve other waves. The model is incapable of resolving other waves. But in reality, the true nature, if you analyze the satellite data in the tropical region of cloudiness or outgoing long wave radiation or sea surface altimetry, where powers are more also focused on other sort of waves which we are not studying here. So anyway, not going without much detail about what are the waves which are not available to us, let us focus on what are the waves available to us. So to do that, what we have did is a very numerical approaching this problem in a numerical point of view. We have shared a model code of reduced gravity model code, which we have simulated using our simplified initial and boundary conditions, if you remember in the last class. So let me open some of the whiteboards we depended in the in the last class. So we have looked at certain wave solutions of initial condition of this form, that we have initialized the ocean with a slab ocean condition in which we have 100-meter thickness, and we have a tropical domain 25 south to 25 north, and we forced this domain with some westerly wind burst, and we looked at some of the solutions formed by that. So those solutions were looking something similar to what we plotted in the last time in the ferret script. For example, in 40th day, we found a solution of this shape, which is coming very soon in the monitor. So this is kind of a wave we have seen in the that we stopped our discussion here. So this is a simulation output of forcing of the ocean given for 1 month. Then the wind forcing is switched off. So the top panel shows how the 100-meter thickness has deviated from those initial conditions. So you can call it as a thermocline. So there's a well-defined Kelvin wave emanated from the forcing region to the east, and there is a couple of Rossby waves emanated to the left, which is shown as the color blue. So they are, the blue means they are shoaled, I mean thermocline squeezed, and the red means thermocline bulged. Okay. So that's the situation we arrived. Then we look at the ocean currents. So Kelvin wave currents looks very parallel to the equator, and Rossby wave currents looks like cyclonic circulation with respect to the thermocline, or with respect to the pressure contour associated with this thermocline. So now we stop the discussion here, because now we need to understand what is going to happen to these waves at the boundary, which I haven't taught in the class. Because ocean is not a continuous domain where zonally connected. They are bounded by boundaries, right? If you look at the major global oceans, there are Atlantic Ocean, Pacific Ocean, Indian Ocean. They all have continental boundaries. In case of Indian Ocean, what are the boundaries? We have boundaries at the left and right, and by the African continent blocks the ocean at the western part, and the maritime continent, the Indonesian Australian landmass, blocks the ocean in the right part. And in the north, we have Indian landmass closing the ocean, and the southern part of the Indian Ocean is open to the southern oceans. So likewise in the Pacific also, if you look at, let us go back to our so sorry, just give me a second. Okay, so in the Pacific also we see similar blocking, right? So let me draw the Pacific Ocean here. So how the Pacific Ocean look like, say for example, so you have a tropical Pacific Ocean, you have a blocking by the Indonesian land masses and the Australia here, okay, and then other land masses blocking here, and in the west we have a blocking by the American continent, okay. So this is a kind of a tropical ocean basin in the Pacific Ocean. So what happens to these waves as it encounter the boundary is a critical question to answer. And what happens to the waves when encounter at the western boundary? So waves undergo reflection. So if you have a boundary, the waves can undergo reflection, but there are certain rules how they can undergo reflection. So for example, a Kelvin wave will undergo reflection at the eastern boundary. And what can happen is that a part of the energy propagates along the coast in the north and south direction. Why? What is the rule of propagation of Kelvin wave? Kelvin wave requires a boundary at the right hand side of the propagation in the northern hemisphere. That's the rule of Kelvin wave. Okay, and it requires a boundary at the left hand side of the propagation in the southern hemisphere, which is true. So that means the waves can propagate along the coast. So what is the direction of propagation shown as this arrowhead? So at the right side of the direction of propagation, it has a boundary. It's the coastal boundary. So therefore, it can propagate poleward. And in the southern hemisphere, what is the direction of propagation? To the south. So if you think in the direction of propagation, it is encountering a boundary at the left hand side, right? So it can also propagate along the boundary. That means the entire Kelvin wave energy, can it propagate to the north or to the south? Yes, it can, but that is not the end of the story. Some part of the energy can also radiate back to the ocean, and when it is radiate back to the ocean, the direction will become westward. So what is the tropical wave allowing you to propagate westward? If you look at the dispersion curve, so let us spend some time in the dispersion curve. The westward waves allowed are basically Rossby wave or mixed Rossby gravity waves. But mixed Rossby gravity waves has certain frequency which is well above the Rossby wave. So according to the incoming frequency of the Kelvin wave, suppose the Kelvin wave arrival is of a very low frequency Kelvin wave, it can go back westward only using this Rossby wave channel, because that's the only dispersion curve permission it has. So accordingly, it will take a Rossby shape and propagate westward. So now there is a critical question comes. Some part of the energy, say for example, X percentage of energy propagated poleward and Y percentage of energy propagated westward. So what is the partitioning between X and Y? So basically X plus Y definitely equal to 1. That means, say for example, 40 percentage or 0.4 of the energy propagated as Kelvin plus 0.6 propagated as Rossby. So total becomes 1. So what is this partitioning of energy with respect to Kelvin as well as Rossby? So to understand that, we need to study the theory of reflection of waves at the boundary. Similar argument can apply in the western boundary also. What happens to the Rossby comes to the western boundary? Can this be, suppose there is a smooth continental boundary like this, can this propagate as a Kelvin wave in this direction and another Kelvin wave in this direction? Let me draw it more clearly so that you don't get, suppose the boundaries available is like this. Assume there is a ocean coastal boundary available. Can the Rossby wave propagate like this? It cannot. Why? The propagation along the coast is in form of Kelvin wave. So here, where is the boundary? The boundary is at the left hand side of the direction of propagation, which is not allowed. Kelvin wave always requires a boundary at the right hand side, because why? F is positive here. The Coriolis or potential vorticity is positive direction. That means it's anti-clockwise in this hemisphere. So that shows by theory, Kelvin wave requires a boundary at the right hand side, not at the left hand side. So Rossby cannot propagate as a Kelvin wave at the western boundary. This is a strong limitation. So what happens to the energy of the Rossby waves when it arrives in the western boundary? The energy has to do somewhere. Either energy has to get dissipated by against the coastal friction, which is not possible because it depends upon the incoming frequency of the energy. If it's a very large waves, no, it cannot get dissipated against the coastal friction. So the other possibility is that it can get reflect and comes back as a equatorial Kelvin wave again. The reflected equatorial Kelvin, it can come back as that, because the dispersion curve shows the Rossby wave get reflected and comes back to the eastward only by as a Kelvin wave. So these are the two waves available in the dispersion curve. It cannot come as the mixed Rossby or gravity waves, because his frequency is much above what than the incoming Rossby wave. The frequency matters, right? It cannot assume a different frequency. It may assume, if you go to the theoretical discussion and how the energy conserved among due to the reflection, it can assume different form, but most likely it can form a Kelvin wave and go to the east. The energy can escape to the east. Let me close this, it's annoying. Okay, so energy can reflect to the east. So that means, let me write down the possibilities here. few possibilities, writing down uh, Kelvin wave at east boundary. Okay, it reflects as a Rossby wave, and Rossby wave at west boundary reflects as Kelvin wave. So they are like a complementary to each other. So this is the kind of rule for reflection. So we are going to see that today in the numerical simulation at least. But this is quite a descriptive nature of lecturing. There is no proof I am giving here. The Kelvin wave will reflect back as a Rossby wave, and the Rossby wave will reflect as a Kelvin wave. So what's the proof? So after looking at the numerical output first, let us go back to theory and find some certain proof or a rule, at least for the component. What is the partitioning of energy under reflection? How much of the energy can go along the coast? How much of the energy can go back as a Rossby wave? And what is controlling that partitioning of energy? There must be some theoretical rule partitioning this energy amongst the coastal Kelvin wave and reflected Rossby wave. Because this is very important. Why? Because this discussion readily has an application in terms of El Nino we are going to study, or we may study in few days. So El Nino is nothing but explained by this reflection propagation of these waves. Okay. So therefore, it is important to understand what is the rule applied for the partitioning of energy among the waves such as Kelvin and Rossby under the reflection phenomenon. So we are going to study that also. So make it simple. Let us go back to our numerical experiment, which is shown here. On the day 40, we have seen that uh, the waves has arrived at the eastern boundary, and the Kelvin wave and the Rossby wave arrived at the western boundary. So now let us go ahead and plot what happens if you advance. Say for example, sorry. If I plot the scenario on the 50th day, I hope some of you at least simulated this model at your side and studied this outcome. But if you don't, then let us see it here. So I'm plotting the situation for the 50th day. What happens? Okay, so this takes the shape of like this during 50th day. The Kelvin now reached the eastern boundary, and the current shows that it is now turning along the coast, or the Kelvin wave is turning along the coast, and current also now developing parallel to the coast. Rossby pretty much arrived at the west, and nothing much happened, okay, on the 50th day. So let us go ahead to study some significant difference. On 60th day, after 2 months of the experiment, let us see what happened. So this is what happened after 2 months of the experiment. The Kelvin now splitting into two channels. You can see from the bottom panel of the currents or coastal currents, it is kind of splitting towards the north and south. Okay, and the wave is more and more impinging on the right, on the eastern boundary. The Rossby some kind of encountering the boundary, but there is no equivalent Kelvin wave produced at the western boundary. Can you see any coastal current building there? No. The currents, if you look at, they are totally different. What happened at the west and as opposed to what is happening at the east. They are looking so different. So let us go ahead little more, advance in time and see what happens. Say for example, 70th day. 70th day, yeah, there is something interesting happening in the eastern boundary. What happens? The coastal Kelvin waves more evolved and started propagating along the coast. That is what seen as some coastal currents at the east to the north and to the south, somewhere around 10 degrees south to 20 degrees south. So I can zoom it. Even if I zoom, it doesn't change the size, but I appreciate if you could pay attention closely. 10 degrees south to 20 degrees south, you see some coastal currents going south. Similarly, symmetrically, 10-degree north to 20-degree north, you can see some coastal current going to the north. But some other anticyclonic circulation also developed. So what is the cyclonic or anticyclonic circulation at the equator? That must be a Rossby wave. If you look at the thermocline, some component has propagated along the coast, which is 145 meter, and some component is kind of returning back to the west, and that is what make this shape something like of an elliptical shape at the east. Okay, what happened to the west? The Rossby wave has no way to escape along the coast as Kelvin wave. You don't see any proof of coastal current, but some strange currents develops around 60 degree east to 100 degree east, where my mouse is pointing, and that currents are westward direction. And if you look at the thermocline, some type of elongation of blue anomaly happened at the west. And that is nothing but the reflected Kelvin component by the Rossby. The Rossby arrived at the west, they're reflecting as Kelvin. Because Kelvin travels faster, right, than Rossby, the reflected components arrived much ahead of 80 degree east by the 70th day itself. And that develops a westward flowing current now, because Kelvin wave currents are parallel to the equator. So if you look at the 60th day back, if you go back and look at the 60th day, you don't have that current. Which current? The current I am pointing my mouse over it. Say for example, 60 to 100 degree east. This current may not be there during 60th day. Let us plot it again and observe it. Yeah, it's not there. It's not just quite started there, but or slightly starting. Or if you go back to the 50th day, that current is not there at all. Perhaps, for example, go back to the 50th day, that current is not there at all. See, there is no such current between 80 degree, around 80 degree east. There was no such current. Suddenly, a westward current developed on the 17th day. Where is it coming from? It is nothing but the reflected Kelvin wave due to the Rossby. You can see in the top panel also like a bullet type of shape emanating from the Rossby to the eastern direction, and some currents built up around 80 degree east. And that's definitely a Kelvin wave reflection by the Rossby. When what happened at the and the Kelvin wave quite quickly come back to the position of 80 degree east and all. Why? Because Kelvin wave travels faster than Rossby. So after reflection, it immediately comes back, and a Kelvin wave current also built up. And the cyclonic circulation at the west is getting more and more cut. So the energy of the Rossby is getting cut, and that energy is propagating back as the Kelvin. At the eastern boundary, a new anticyclonic circulation developing. So the eastward propagating Kelvin wave reflects as Rossby wave. And the sign of the wave is same. A positive Kelvin wave reflects as a positive Rossby wave. A negative Rossby wave reflects as a negative Kelvin wave. The sign doesn't change. So the red is red and blue is blue, right? You can see here. Let us go ahead and plot further and study what happens at the day equal to 80. So 80 means almost 3 months, right? So now you see, yeah, the Kelvin wave almost propagating along the coast. A part of the energy has propagated northward, a part of the energy reflected. So here, by looking at the amplitude of the thermocline, the Kelvin took a larger share along the coast, and Rossby get a smaller share, maybe like 30% of the energy reflected back as Rossby. I'm talking about the red wave, okay, red color wave. Maybe 60% of the energy propagated as Kelvin to the north. So I mean, looking at simply by looking at in the layman's perspective, the amplitude of the wave. A piece of Kelvin now going along the coast to the north, a piece of Rossby now reflected and going to the west. What happened to the other guy, the Rossby? If you look at the currents, the cyclonic circulation in the earlier at the western boundary completely disappeared. Now they all turned back of a strong Kelvin wave at the equator. Look at the currents. They are strongly parallel to the equator, but the direction reversed by because it's a blue Kelvin wave. It's not a red Kelvin wave anymore. So if you look at the pure geostrophy balance, you can assume if low pressure at the equator and high pressure on either side, the current has to flow parallel to the geostrophic, pressure contour, which is westward direction. If you apply simple geostrophy, you can find the direction of the current. So now the equator has a strongly reversed currents flowing to the west, okay, and the waves from the west propagating to the east, and the Kelvin wave along the coast propagating to the north, and the cyclonic circulation, anticyclonic circulation around the positive Rossby wave in the eastern boundary. You can see you can capture it from the currents here where my mouse is pointing or mouse pointer is moving around. Let us go ahead, see what happens on the 90th day. That means 3 months after our experiments. What happens? The picture is more clear that Kelvin along the coast further proceeding to the north, the Rossby proceeding to the west, and the blue Kelvin almost reached at the center, and it also hit the eastern boundary now. So it straddled the Rossby and penetrated in between and gone all the way to the eastern boundary. So now they make a two Kelvin and Rossby. So this is now going to happen like a pendulum, up, left and right. Okay, so this will be keep happening like the reflection, and some part escaped to the as a coastal Kelvin wave. Again, now the Kelvin wave which comes from the Rossby all the way reached the eastern boundary because they travel at 3 times faster than Rossby. So again, it started reflecting. So this is the reflection of waves at the both the boundaries. I think better we will see this one more advance in time, say for example 100th day or 120th day, 4 months after. Let us see what happens the solution after 4 months. After 4 months, this is how it looked like. The earlier Kelvin has propagated all the way, reached the northern boundary and southern boundary. Another two Kelvin started, and the reflected Rossby now has moved to the left. New Rossby may develop due to the reflected Kelvin, and all these things are keep happening. So the amplitude of the wave now, however, going to reduce because the forcing is removed. So this is free wave oscillation, right? So now one strong Kelvin is seen at the equator. If by the currents, you can capture it. So going further, examining in time does not make any sense. Let us let us conclude here and see the the continuous evolution of the wave as a movie that will be able to that will enable us to understand the in a single shot. Will able to understand. So this is what happens. Let me begin the movie again. This is day one of our experiment. I have compiled all the images into a movie, so you can see how fast it propagates, and the direction also you can see. So if I go ahead with the movie, so this is what happened on 1 month, happened in 1 month. The same thing, I convert them into movie. So here you see a Kelvin and Rossby fully developed at 1 month. Then Kelvin wave is not now going to move to the eastward direction. You see, this is the 45th day. Kelvin and Rossby separated, and they traveled to the eastern direction, and then they taking a poleward propagation. On 67th day, you can see they are taking a poleward propagation. In the west, they are not taking any poleward propagation. Rather, it's going to come back. It's going to come back. So this is what happened. So what happened in the eastern boundary, say 87th day, the Rossby wave has reflected and some has propagated along the coast. Okay, so this is a kind of an interesting situation, and partitioning of this energy we are going to study in a while. What is the rule of partitioning of energy, Kelvin versus Rossby in the eastern boundary? And then let us keep playing this movie. You can see that the reflected Rossby coming to the westward direction, more and more reflected Rossby going to come. So this is what in 190th day, 200th day, 230th day. So the amplitude of the wave is diminishing because why? There is no more forcing. So they are freely propagating wave and diffusing against the background diffusion of the fluid, and there is no waves at 360 day. The ocean has settled back to rest, which was initially 100-meter thickness. So 100-meter thickness I am showing as a white color. 95 meter to 105 meter, you only see a white color. Anything above than that, you see as a color. So let us play the movie again. Let us see what happened in this experiment. By forcing the ocean, you know, you know, initially completely rest ocean with some wind bursts at the equator. These are the kind of wave emanating, Kelvin, Rossby, and etc. So I hope you understood by these simple experiments about the tropical wave, how they set up dynamics in the ocean. So understanding of this is very important because this is exactly what we are calling the theory of El Nino. So I'm going to explain that in a while how this is connected to El Nino, because this reflection of the wave and coming back as another wave and meeting each other, they have some capacity to kill the signature, because the positive Kelvin wave reflects as positive Rossby wave, the negative Rossby wave reflects as negative Kelvin wave. So they have some kind of an interaction after some time, which can kill the anomalous signals each other. Okay, so that is the central discussion part of the El Nino theory. Okay, so that's good. So this code is provided to you. You can do another experiment. Suppose if you simulate the same with reversing the direction of the wind. So here I have forced the westerly wind. The wind burst is given as westerly coming from the west. You can change the code and make it an easterly wind and study what happens. You can plot it at different days of evolution. See what shape of the Kelvin changes and what the sign of the Kelvin changes or the sign of the Rossby changes. But what happens? Are they still propagating east or are they propagating in an opposite direction? It doesn't happen. Theories say the Rossby always has to go westward direction. That's what the dispersion relation teaches us, and Kelvin has to go the eastward direction. So you can examine by looking at the changing the direction of the forcing in this particular experiment and study yourself what happens to these waves, how they move around, etc. Okay. So saying so, let us come back to the theory that what happens at the boundary. We have now studied a little bit here, but now we haven't fully discussed what happens at the boundary and what happens at the why this motion is restricted in the tropics. I mean, although we have said in the beginning the tropical dynamics is kind of a restoring dynamics due to the change in planetary vorticity. But where is the proof that we can say these waves are restored within the tropics? So that is one thing to consider. And another thing is that maybe I can pose the question more clearly in this movie itself. Say, for example, let us play this movie. So what are the waves which is allowed it to propagate far away from the tropics? Only the coastal Kelvin wave. Otherwise, the energy is trapped well within the tropics. Do you agree that? Yeah, you can see that other than the coastal part, the Rossby part or the other parts are trapped within the domain of 20° north to 20° south. So don't look at the coastal Kelvin wave which is happening along the coast. That is because there was a coast, that's why it's propagating. If there is no coast, it is not able to propagate. So what the question I am posing here is that we begin our discussion, the tropical dynamics confined well within the tropics. Is it true? It is true because see the Rossby wave, they are not elongated all the way to the 20 north or 30 north or going ahead like that. It is constrained within the tropics of 10° north and south in this example. And if you look at the other elements developing 10 north or 15 north, they are not propagating to the here. For example, see, this is a typical example I want to discuss. Look at the waves. They are well defined, confined within the 20 north to 20 south. Don't look at this Kelvin wave at the boundary, which is hitting along the boundary, because there is a boundary that is. So if I'm in my experiment, I cannot keep the boundary infinitely long because I have to stop the simulation at some place. And because of artificial boundary, these waves are moving around. Suppose there is no artificial boundary here, this Kelvin wave on the top and bottom of this graph, you will not able to see. I hope you understand what I'm discussing about. Here, see my mouse pointer, if you can see. There is a red color wave moving to the west, must be a Rossby. Another blue color wave moving to the west, another Rossby. And there is a oval shaped structure straddling between equator or 5° north to 15° north. So they all are confined within the tropics. Don't look at this Kelvin at the boundary because there is an artificial boundary. 25° north mein kuch there is no boundary there, right? There is artificial boundary. That's why these waves are occupying that area. If there is no boundary, there is no way this wave can reach here. So assume, forget about that 20 north above and 20 south above, the artificial boundary. All other solutions are confined within the tropics. And why? That is exactly we started discussing. There is a boundness of the system with respect to tropics. The numerical experiments giving you a proof. True, it is true. The Rossby here is not going all the way to the north or all the way to the south. It is confined within the system. This is because of the eigenmode solution of the problem. This is certain eigenvector. The solution is the wave number in the meridional direction has to oscillate within the confined domain, also allowed by the mode number given from the Hermit polynomials, -1, 0, 1, 2, 3, etc. So that kind of bring the solution close to the equator. So there must be certain rule up to what extent a tropical dynamics can go beyond the equator. So that, another way of speaking, there must be a critical latitude where the dynamics is bounded. So what is that critical latitude? So that's what I am going to discuss further in the theory today. So to understand the critical latitude concept, let me pull up a note here. Let us examine what is critical latitude and equatorial wave guide. So within this critical latitude, all the waves are guided within the tropics. So to arrive the critical latitude concept, let's go back to our fundamental relation. If you remember, the three shallow water equations, the U velocity, V velocity, and the mass conservation equation, we have reduced in terms of V, if you remember. And we applied the most generic form of the solution, V equal to V naught exponential I kx minus omega t. So when you substituted, you arrived at this equation. From here, we found the Hermit polynomial and associated solutions. Okay. So in this equation, it says that as for V tends to 0, as Y tends to plus or minus infinity, that means the equatorial beta plane, the dispersion relation says the second part, right? Omega square by c square minus k square by minus beta k by omega equal to 2n plus 1 beta by c, where n is the different modes of meridional modes of the wave. This we have already seen in the previous lecture. So where n equal to -1, 0, 1, 2, 3, etc. From where here is what we built up all the Kelvin, Rossby, mixed Rossby, gravity, everything we built up from this relation. Okay. Now, on the other hand, the equation 1161, which is this fundamental equation, can also be written as this part can be 0 for this equation to be 0. So if you follow in that direction, so omega square by c square minus k square by minus beta k by omega equal to beta square y square by c square. From this equation, putting this term equal to 0, because V vanishes as Y reaches infinity. So for a critical latitude, this assumption is good enough. V equal to 0 means this has to be 0 also, right? So from that assumption, I can replace my Y with YC. What is YC? Critical latitude. Y is actually the meridional distance away from the equator. So we can call it as a latitude. Okay. So at a critical latitude YC, so beta square Y square YC square is equal to the Y suffix C. Okay. It's not Y multiplied by C. C represents the critical latitude is equal to this one, which is by the previous equation equal to 2n plus beta by C. That means at the critical latitude, the relation of the dispersion is beta square Y square C YC square is equal to 2n plus 1 beta by C. What does this tell you? That means Y square C square, YC square is equal to 2n plus 1 C by beta, because beta cancels from each side. So this is the fundamental relation. This is the relation at which a wave can penetrate in the tropical domain. Critical latitude, that means because V has to disappear at Y tends to infinity. Using that relation, we arrived at critical latitude exists, which is what you are seeing here. A critical latitude beyond which the solution are unable to penetrate, except the Kelvin wave part. Don't think about it. That's a boundary wave. That's an artificial boundary in the model. That's why there is an artificial wave. Otherwise, there can be no waves beyond 20 north in this situation. Okay. So except that, all the solutions are now bounded within the tropics, close to the equator, and that is why we are discussing discussing here. So YC square is equal to 2n plus 1 C by beta. That means for a first baroclinic, because the speed C, I think by now you know what is the speed C means. It is the gravest mode of the system. For a barotropic mode, it is equal to square root of GH. For a baroclinic mode, it is equal to square root of G dash H. Now I can use the word G dash with confidence, because we have taught that what is G dash. It is nothing but the reduced gravity of the system. If you have a density stratification, the stratification is going to govern an additional dynamics in the system through which the wave can propagate, and that is G dash. G dash is much lower than the real G, therefore the wave can travel slower. And the most important baroclinic speed is the first mode, which is approximately 3 meters per second in the ocean. And if I take a beta is equal to 10 to the power minus 12, and for meridional mode, n equal to meridional mode, okay, Again, meridional mode is different from the baroclinic mode. These two modes I have shown as a mass spring system, one as an arc and one as a vertical system in the last class, if you remember. So for a meridional wave mode, n equal to 1 and beta equal to this and c is equal to this, y critical latitude comes around roughly 3000 kilometer. That means roughly 30-degree latitude. So that is the maximum extent of the latitude the solution can confine, and that is very beautifully come as the tropics plus or minus 28-degree latitude. So that is the area by which the situation is bounded. So this beyond the critical latitude, the wave cannot penetrate, it will reflect back. So these critical latitudes of tropics acts as a wave guide for the tropical dynamics. So that's why called equatorial wave guide or tropical wave guides, beyond which the solution cannot propagate. The story doesn't end here, but this relation is a kind of a poor relation. Why? Because it does not tell you about the frequency of the wave. It tells you only about the baroclinicity of the system and beta, but it is quite blunt. It doesn't tells you any other information. What other properties of the wave can penetrate this critical latitude, or what are the maximum extent of this critical latitude for any frequency of wave, or is it same for all frequencies? What are the frequencies you are talking about? Like can be an annual wave, semi-annual wave, intra-seasonal wave, much short frequency wave, much high frequency wave. All these waves has the common critical latitude. So that is not kind of got by this relation. So which is therefore it is a kind of a poor relation. So let us look at another relation. So here, therefore, YC is the critical latitude or the turning point for tropical waves. Similarly, one can prove for the maximum frequency of a long wave in the long wave limit as k tends to 0. One can also prove this. If you manipulate these terms, you may also arrive the omega max, the maximum frequency is equal to c by 2yc. Here there is some more guidance regarding the frequency of the wave. So as in the long wave limit, the maximum frequency possible is related with the c by 2yc. That means the frequency is inversely proportional to the critical latitude. That means a lower frequency wave, critical latitude increases. What does that mean? A lower frequency wave like an annual wave or higher wave can penetrate at a larger extent away from the equator. However, short frequency wave like for example, annual Rossby wave may exist at a latitude up to 40-degree north. That is the relation says the wave frequency is inversely proportional to the critical latitude. So as the wave frequency decreases, the critical latitude increases. That means it can penetrate or present even at a place of 40-degree north. But if the frequency increases, its extent more and more bounded towards the equator. This is a very interesting thing actually. So that's what I am saying. This wave can be assumed as certain meridional wave number. The large waves with a large meridional wave number may extend beyond 30-40-degree north. But as you come closer and closer, I mean shorter and shorter waves, a high frequency wave, like a semi-annual wave, your critical latitude is more closer to equator. For intra-seasonal wave, the wave seldom escapes certain latitude of 10-degree north or south. So that means, suppose, let us take an example as a schematic. Okay, a schematic is easy to learn for students, for example. So let me take a new page. Let me draw a situation happening in the where is my pen? Yeah, in the maritime continental area. So this is a quite critical or situation always have. So this is the Australian continent. So my drawing may not be very accurate. Okay, this is Australia. Okay, and this is the Java Sumatra area. Why I choose this area? Because this happens very often in this particular location. This is Java Sumatra area. Okay, so Java Sumatra coast. Oh, this is basically Eastern Tropical Indian Ocean. So now what happens is that suppose there is a high frequency forcing of wind with alternating sign. Same answer, for example, very high frequency forcing. So if I draw a high frequency forcing, I can draw something like a intra-seasonally oscillating wind is forcing. So this can emanate certain certain waves, say for example Kelvin waves, they will always often see around propagating around the Australian coast. This is a common feature in this particular area. Now, if the frequency of forcing is annual, say for example, this wave can go anyway. Kelvin wave along the coast, it can go all the way here, but it on the way it goes, it can emanate Rossby waves. Okay, in this particular shape as Rossby waves. This going to emanate here. So if I, because it's an oscillatory future, the emanating Rossby wave will also have a positive and negative sign. So this is kind of a waves it going to emanate. Okay, if it's an annual frequency, it can emanate as south as 40 degrees south. But if it's a very short frequency wave, the Kelvin wave goes all the along, but Rossby wave will be restricted within this belt. So it has to emanate here for a very high frequency waves. Okay, so the high frequency wave cannot be emanated at a higher latitude because there is a restriction as per the theory. For annual waves, it may emanate the Rossby wave at a critical latitude of 30, 40 south, but in the previous example, but for a high frequency intraseasonal wave, the energy has to shed out of it at a much lower latitude. So where is the equator in our problem? If you are not familiar, the equator comes around somewhere here. This is the equator. So this is the equator. So now you get the sense of it, equator. So this may be around 20 degrees south, 20 degrees south, and this is 40 degrees south. So an annual wave, for example, annual forcing, okay, in the Pacific may emanate Rossby waves in the west, in the Indian Ocean at a higher latitude, but a semi-annual or ISO intraseasonal oscillation type of forcing can emanate Rossby wave in the much lower latitudes. So this is all related to the relation. The maximum frequency is inversely proportional to the critical latitude. So as the frequency increases, okay, or the W, you don't call say maximum, W is inversely proportional. So as frequency decreases, critical latitude increases. That means it can penetrate all the way to the south. That's the reason the annual Rossby waves are seen in the ocean mostly where the annual Rossby, if I erase this picture, this is the Indian Ocean, 40 south to equator. Usually the annual Rossby wave in the sea surface altimetry, what is the annual Rossby wave? The period of the wave is annual. That means 1 year kind of period of the wave. So you see a large blob of wave. Wave means I'm talking about the sea surface height here, because that's what we are familiar with in our previous experimental. Sea surface height is what we were discussing. Such type of large shape of sea surface height you can see, anomaly you can see in the ocean. So this is basically, we call it as annual Rossby wave. So this is the trough of the wave, this is a crust of the wave, the total wavelength lambda may be assumed as this. If it is a single wave, but not necessarily it's a single wave, this can be a group of waves. But anyway, this is kind of a annual Rossby wave structure you see in the equatorial tropical South Indian Ocean. Now there is a critical question I have to ask: why I did not draw the face of the wave in this direction in my example? Why I try to incline it towards the left? I mean, I inclined it towards the more left as I go more to the equator. Can anybody guess why I have drawn a face like this? Which is true. Which is true actually. If you see our movie, see the inclination of the wave is more towards the left. The face of this is a typical face of the wave. Okay, more towards the left as you go closer to the equator. Why I draw it purposefully like that? Can somebody guess? Well, it is because you all know the speed of the Rossby wave increases as you go towards the equator, and speed decreases as you go away from the equator. So for a given wave, say for example, wave of, let me draw a wave just at the starting. If somebody perturbing the ocean of a given form of something like this, if somebody perturbing the ocean with a wave shape of like this, you are, suppose you are placing a mass something like this. So this is in the north south direction, sorry, north south direction you are placing the perturbation, right? But it will not remain like this as it moves in the space. It will not remain, rather it slowly started inclining to the left. The reason is that as you go closer to the equator, the waves travels faster than as you go away from the equator. That's why there is an inclination you see here as you go closer to the this part travel faster than then you may ask, isn't it one wave? There is no guarantee that when you perturb the ocean or place some mass on top of the ocean, it's going to govern under the dynamic of just one single wavelength lambda. There may be an infinite number of possibilities of wave number here, and accordingly it can take the speed. So this is how what you will see, the wave is traveling faster towards the equator. I mean, as you go towards the equator, wave travels more westward because it travels faster, and it travels slower as you, and there is a relation for the speed with the critical latitude with the latitude also. So if you manipulate your dispersion relation, say where is your dispersion relation, so if you modify your dispersion relations, you will get that similar relation also. You can calculate the speed of the wave with respect to latitude. So the speed increases as you go away from the I think that can be proven much easily if you look at the dispersion relation of what is a Rossby wave dispersion relation. Speed of the Rossby is equal to minus beta by k square plus 2n plus 1 beta by c. So from here you can build a relation for the latitude or you can take 2n plus 1 as the meridional wave number. Okay, you can take it as L square. Assume k square is equal to 0, then CR is equal to minus C by L square. You can approximate it. You can calculate the speed of the Rossby with the latitude if you manipulate the dispersion relation. I'm not right away getting the relation, but you can do. But this is what happens. The speed of the Rossby increases as you go away from the equator, as you go towards the equator, and decreases as you go away from the equator. And that's why this kind of a inclined shape one is drawing. Even if the initial condition, if suppose you place a mass at t equal to 0, at a t equal to t1, it's going to look like this. It's going to propagate more faster here and slower here. Okay, so that's going to happen. So anyway, why I come to this discussion here, because the critical latitude is so important, because it is proportional to the frequency of the wave. So the annual frequency type of signal or a annual seasonal cycle can emanate a Rossby wave far away from the equator. And for example, in typical Indian Ocean Rossby wave structure, if you look at the sea surface altimetry, you give. Hello.
Hello.
Anyway, I heard some background noise. Anyway, so if you perturb the, I mean, if you see the sea surface altimetry of the southern Indian Ocean, so you will see that the waves aligned in this particular fashion. Okay, so that's why the discussion of the critical latitude came today. So the critical latitude is that the latitudinal extent, you may call that the latitudinal extent at which the tropical dynamics is constrained with respect to the equator is called the critical latitude. And that can be proven by theory that it is proportional to the frequency also, rather inversely proportional. Low frequency wave can penetrate far away from the equator, but high frequency wave, more and more high frequency, they constrained, restricted within the vicinity of the equator only. Okay, so these are some theoretical consideration we are considering today. So this simple toy model is very useful. You can configure the model with not only the forcing of Gaussian wind forcing we described here. You can force this model with other idealized forcing. I have given some idealized forcing in the code already, or you can make some kind of idealized forcing for yourself. You can take this model to the mid latitude just by changing the central latitude. You can put it in the 30-degree north and see a mid latitude domain, how it works under the constant wind forcing. You can generate a gyre circulation and the Munk layer, for example, western boundary intensification. All you can study with this model. This is all up to you. You go and explore it and try to understand more about the ocean circulation using this model. So I think that is a decent explanation about the tropical dynamics. So the next part we have to look at is the promise that I have made. I mean, what is the rule we have to say the amount of partitioning of energy under reflection? Say, for example, I was illustrating in one of the pages earlier. So I think it's in the previous page. Here. What is the rule of this partitioning of energy under reflection? What is the theory based on that? That's what we need to consider next. So we have to look at some paper, for example, the reflection of wave from the eastern and western boundary. So the paper I am going to depend on here is that taken from, I'll share it here, this paper. So what is this paper? This is a paper written by Alan Clark in 1983 in Journal of Physical Oceanography. The reflection of equatorial wave from oceanic boundaries. It's a very nice classical paper, highly cited paper, describing how the reflections are established when the wave hits the east and western boundary. And they give the proof why a Kelvin wave has to reflect as a Rossby as well as a coastal Kelvin wave, and why a Rossby reflect as a Kelvin at the western boundary, and what are all other waves, for example, mixed Rossby gravity waves. Suppose if it hits the coast, what happens to it? And so all the reflection criteria that we are going to study here. So I am going to read a little bit about the abstract here. This paper I can share with you, or you can also download it yourself. So this paper says that the theory is developed to discuss the reflection of long equatorial waves from ocean boundaries. So the main results are as follows. The energy flux reflection coefficients for the reflection of equatorial waves from the meridional eastern and western ocean boundaries have been plotted as function of frequency. So now they are discussing what are the frequency, or I mean, the frequency is going to determine whether the wave is going to quickly reflect back, or whether the wave is going to continue far away from the equator. So here they say the energy flux reflection coefficients for the reflection of equatorial waves from meridional eastern and western ocean boundaries have been plotted as a function of frequency. The coefficients enable one to determine, for example, how much energy of an incoming wave of frequency omega is transmitted along an eastern ocean boundary as poleward propagating Kelvin waves. The coefficients are useful for both modal and vertical propagating descriptions of equatorial waves. As an example, the reflection of the NI waves observed in the equatorial Pacific is discussed. What is NI waves? Mixed Rossby gravity waves in connection with the poleward propagating sea level along the Southern American coast. And the theory further says the Moore 1968 showed that the reflection of an incoming equatorial wave at an eastern meridional boundary consists in part a poleward propagating Kelvin wave. This is what we saw in the movie today, right? Here the same result is generalized in a non-meridional small curve. They have not only describing the reflection in the flat boundary, but some curved boundary also. Then more discussions are followed. So that's what this paper is talking about. So this is a very nice theoretical paper. If the people who are interested to solve things in analytically can go through this paper, and starts with a description of the shallow water equation. And here the treatment is in terms of energy. So how do you get energy of a system if you have a shallow water wave equation? I hope you remember from your GFT discussion, perhaps how to find the energy of the system. So the energy of the system is usually found. What are the fundamental equations we have in our GFT discussion here, shallow water equation? So you have a dou u by dou t component, which is an acceleration component, minus a Coriolis component, right, equal to minus g dou eta by dou x. Now, if you multiply the first two terms with the u, you are going to get a term for u square and uv. This is actually the kinetic energy part of the system. And if you multiply and integrate this equation over the entire depth of the fluid, or you multiply with the h, what you get? You get the total potential energy of the system, eta h. So this is how we calculate the energy of the system. So we have to manipulate this equation by multiplying with the u in the velocity component and to integrate the equation for the entire depth of the fluid. Then you get the potential energy. So the sum of the kinetic energy and potential energy will be the total energy of the system. So some people some people solve the equation of shallow water equation in terms of energy also. Rather, it is better because energy is more conserved under the potential vorticity surfaces, right? It's not necessarily the momentum, because potential vorticity has the three components, as you all remember from your fundamental study. One is the component theta plus planetary component, and another is a weird component due to baroclinicity. This is something really disturbing. So because of this combination of total potential vorticity pi, it is not readily the momentum is conserved, rather you can call energy is conserved. And in that case, the treatment of energy is better than momentum because the potential vorticity has a weird shape here. Because what is vorticity? It is nothing but the tendency for rotation, right? There are various rotation in this frame. The fluid itself can rotate within it, which give you relative vorticity. The fluid, the frame is rotating F, this gives you F, right? The frame is rotating, Earth is rotating, and the fluid has stratification. This is more weird aspect also. Suppose if you have a stratification, so what is a stratification? Say, for example, you have a density structure stratified in this form. This is very common in the ocean, say row 1 and row 2 and row 3. Correspondingly, your pressure surface has to align in an angled manner. So that means the del P and del rho, that means what is the del rho vector here? The del rho vector is something like here, del rho, and del P, which is the pressure gradient vector, is a del P here. They have an angle. So always this system try to tend to be in a non-zero angle. The del P and del rho wants to be aligned parallel. So because of that, this guy has to rotate. So that gives you an additional rotation. This is called the baroclinic vector, right? Baroclinic vorticity. Baroclinic means due to density stratification. So this is P contour, right? P1, this is P2, this is P3. So this is called the baroclinic vorticity. And this offer you another type of rotation, which is what coming in the in this here. I write it neatly: theta plus F by rho times del lambda. Well, lambda is nothing but a function of temperature and salinity, you can call it, or the temperature and pressure, for example. Okay, so that's lambda. So this is the total Ertel's potential vorticity. You probably might have studied. Okay, so this have three rotational components: rotation of the fluid, rotation of the frame, rotation due to stratification. So these three are coming as a combination. So people treat rather energy as a conserved tracer to study the GFT. So in this paper of Allen's Clark's paper that we are studying here, also treating energy as the quantity to study. So you have to go through the theory. I'm not going to teach. So here you can see that they're multiplying U with the U velocity, and total pressure is, and I mean the one H is integrated to get the potential energy. So I'm not going to teach thoroughly here, but I leave it as an assignment to you. So what I'm going to say here, they are also describing the theoretical dispersion curve, Kelvin-Rossby and inertiogravity waves. The most critical part to understand here, I think it's already 3. Should we take a break here? Probably we can break and come back to the discussion of reflection. So we'll take some 10-minute break.
Okay.
Yeah, so we'll regroup here at 3:50.
3:50.
Okay. Yeah, thank you.